When we read different things, our brain does different things. This much is a given. The real question is, what does the brain do differently? And the truth is, we're not sure yet, but we found some good patterns.
One metric that we can use to measure how the brain processes language is the amount of time a person spends reading each word in a piece of text, a metric called the reading time. If a word has a particularly high reading time, that means it was surprising and carried a lot of new information. We can use this to find situations in language where a person would do more processing, which gives some insight into how humans process language. Text is more surprising and thus takes longer to process, the less likely it is to occur in its context. And one way that we can predict or calculate this probability is with computational language models. From classic models like n-grams to modern tools like transformer-based large language models. These models can give a probability for each word in a piece of text. We can then take the negative log probability of this word to gain a new metric called the surprisal.
Surprisal can be understood as how surprising a piece of text is, or, from an information perspective, how much information this word or token provides to the reader. It turns out that the calculated surprisal of a word is proportional to many psychological effects, including reading time.
Words that are very unlikely have very large surprisals and take longer to read. To get a more concrete understanding of this idea, we can look at an example of a very surprising type of sentence, garden path sentences. This is a garden path sentence in Chinese. 咬死猎人的狗是熊逃跑的唯一出路. It is the only way for the bear to run away that killed the hunter's dog. The initial interpretation of it may be 咬死猎人的狗, the dog that killed the hunter, is the subject, and we expect a verb next. However, 咬死猎人的狗, killing the hunter's dog, is actually the object, describing the only way for the bear to run away. And the way here is actual subject. As in, for the bear that killed the hunter's dog, this is the only way to run away.
And here is an example of a garden path sentence in English. The horse raced past the barn fell. At first, we think that the subject is the horse, but it is in fact the horse that was raced past the barn. As the reader goes through the sentence, they build a syntax tree that represents its structure. But then, when they encounter a key word, it turns out that the syntax tree was incorrect, and they have to rebuild their syntax tree. So this is a very surprising word. It totally reshapes how they understand the sentence and provides a lot of new information. A language model would give this word a very low probability and a very high surprisal. Any human reader would have a significant pause at this point.
So in this way, we can use language models to predict human psycholinguistic metrics. Research has shown that, as language models have improved over the years, that is, as they have sounded more and more human, they have also gotten better at predicting psychological effects, like reading time. If you take words that these better language models find surprising, they line up with words that human beings spend more time processing.
This was the general trend until we reached the transformer model. New research in the past year has shown that the large language models, like ChatGPT and Llama, are not very good predictors of reading time. This implies that despite these large language models sounding much more human, their quality is very high. They do not predict how humans process language. A few theories on this discrepancy highlight the fact that large language models learn language from vast amounts of texts, sourced from a huge variety of writings, while humans learn language incrementally and from the community that surrounds them.
As research develops further on these large language models, we can see how and why they don't always line up with how a human would process language. In what cases does the surprisal provided by a transformer-based large language model not correlate with the amount of time a human would take to read that word? And what might that say about how we understand language?